will present my Physics 2, Lab 6, about magnetic molasses. The purpose of this lab is to exemplify the physics behind Faraday's law and how this can create currents when the magnet is moving. This is Faraday's law. The principles in actions are Faraday's law, which describes how a changing magnetic field can induce a current and an EMF into a loop of wire, or tube in this case, and magnetic fields, which describe how magnets create magnetic fields based on their north or south pole alignment. So the experiment. The object selected to analyze was three pieces of magnets stuck together. The time it took for the magnet to fall was recorded, and the length of the tube was measured with a ruler. Here's a video of the experiment. As you can see, it slowed down when going through the tube. We repeated the experiment 5 times. So the system here is the magnet, which is falling down with increasing velocity, which is increasing magnetic flux, and it creates a current in the tube. The tube has an induced current, and the current opposes the change in flux. This current causes a force to the magnet opposite to gravity, slowing it down. Now the computational model. The length of the tube was 0.5 meters. The width of the foil was 1 centimeter, and the inner radius of the foil was 2.5 centimeters. Here is the graph of the velocity versus time for this computational model. Now here's a video of the code. As you can see, here are all the variables such as the length. Now we have the formula to calculate the magnetic field from a dipole, and here we did a formula to calculate the d flux at each point in the tube. And now, as you can see here, the magnet was falling and the velocity remained constant, which meant that it was slowing down. The comparison is that both fell slower than free fall, and the differences were that the simulation lasted about 0.1 seconds more than the average of the experiments. The possible sources of error for this is that the time of the magnet falling was too fast to measure it accurately, and the assumptions were that we ignored air resistance on a moving object and only assumed that each ring had a current caused by the change in flux, but ignored self-inductance. So what if the resistivity of the conductor were reduced as close to possible to zero? How would the dynamics of the falling magnet change? If the resistivity were reduced as close as possible to zero, the current would have to be much larger, therefore creating a stronger magnetic field at each point and slowing the magnet even more. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? This would affect the rings in the model because not at every point there would be a ring, so we would need to create a complicated model where current doesn't just go in rings, but in other shapes. Here's the link to my simulation, and thank you.